Welcome back. Today we are going to talk about a type of problem that is called a ballistic pendulum. This type of problem combines both energy and momentum. And we'll recognize energy because we're seeing some sort of a change. We'll see a change in height or a change in speed or a change in the stretch or compression of a spring. That's how we recognize energy. And then we'll know its momentum when we see a collision. So these are our key factors when we're identifying which of my physics toolbox should I apply to a problem. Here's the setup of a ballistic pendulum. The idea is something like this. Possibly a spring-loaded launcher would launch a ball. And so it starts off with the spring totally compressed. And then afterwards, the spring launches the ball so that the ball is moving. Then that ball that's moving gets caught by a hanging catcher that's hanging from a device possibly connected to the ceiling. And so this ball is going to hit into this catcher, and then the two of them will move together as one. So I'm going to redraw this picture off to the side here, where this ball and this catcher are now moving together as a new object. So once the ball hits into the catcher and the two of them move together, this catcher is able to pivot, and it swings up to some final height. And so in this problem, sometimes the goal would be solve for this height that the catcher goes after the spring has launched the ball. And sometimes we could even work it backwards. Knowing the height that the catcher goes, find how far this spring had to be compressed in order to make this whole thing happen. So we could work this problem forwards or backwards. But the idea is, in the beginning, this ball is at rest attached to the spring. And in the end, the ball and the catcher move together as one up to a new height. When we are solving problems like this, again, it's all about recognizing where is my energy. There's a compression of a spring. Here we go. I've got some energy. It changes its height. At the place where it changes its height, I should be looking at some energy there. So I'm seeing energy at the beginning. I'm seeing energy at the end, and it's very tempting to take the energy at the beginning in green and set it equal to the energy at the end in pink, and to completely disregard what happens in the middle. But what happens in the middle is important. What happens in the middle is a collision. When the ball hits the catcher and the two objects move together as one, this collision occurs, and we have to take that into account because we notice that in this inelastic collision, that the kinetic energy is not conserved. What does that mean? That means that the energy present in the green portion is not going to be equal to the energy present in the pink portion. Some of the energy is lost to the surroundings during the yellow portion. So how do we attack this problem? Well, we have to break it into 3 steps. Step 1 is going to be saying, well, from the spring to the motion right here, I can use energy. I can see that this initial status right here and this final status right here, that there is no collision that takes place in between, that there is no outside force acting on it. And so I can take all of the spring energy stored in that spring to begin with, and I'll say that that's energy that the spring had, and I'll say all of that energy turns into kinetic energy of the ball afterwards. I can say that the spring energy the spring was storing 100% of it gets transferred to the kinetic energy that the ball has before the collision. So I could set my 1/2 k delta x squared equal to my 1/2 the mass of the ball times the speed of the ball before the collision squared. Okay, so let's call this V1 maybe for the speed before the collision. And let's call this mass of the ball M1. And so we can set the spring energy equal to the kinetic energy here. But that energy is not going to all be accounted for in the pink region. Some of that energy is going to be transferred out of the system during the collision. I have to do the second part here as a collision. The second part is going to say, I am going to use momentum during the collision. I am going to draw my before and after picture. A ball and a catcher, and then the ball and the catcher moving together. And I'm going to say that the momentum of both of those objects added together has to be equal before and after. So M1V1 plus 0, because this isn't moving, I guess we can go ahead and call it M2V2 for now, equals M1 plus M2, all moving at their final speed, V prime. V prime is the V after the collision. Turns out that this is 0, and this velocity right here is this velocity, right? The speed that the ball has leaving the launcher is the speed that the ball has entering the collision. However, the speed that the ball and the catcher have after the collision is really what we're going to care about for the after the collision process. Basically, what I'm saying is the energy that was present right here, the 4 bars of energy we had present here, that after a collision, our mass went up, our speed went down, we have lost some kinetic energy. Right now, we could talk about the kinetic energy before the collision and the kinetic energy after the collision. And we could say that the kinetic energy before the collision was all 4 bars, and that the kinetic energy after the collision is only 3 bars. We have lost some kinetic energy. The ball has lost some kinetic energy. We can say that some of that energy was dissipated to the surroundings. But really, as a result of this collision, I am working with less kinetic energy. The kinetic energy I have leaving the collision is going to be found, and that kinetic energy leaving the collision is going to be 1/2 both masses added together times their speed after the collision squared. Why is that important? Because really it's this energy that's equal to the gravitational energy at the end. When we are doing step 3 here, step 3 is to say, I see that this kinetic energy from step 3, I have all of this kinetic energy, not 4 bars anymore, but 3, because the collision took some of that energy away. So now I have less kinetic energy to deal with, but that kinetic energy that the ball had is going to then turn into gravitational energy that the ball and the earth share. And I'm going to be able to set the kinetic energy after the collision equal to the gravitational energy at the end. So I will take my 1/2 of both of my masses added together times their speed after the collision squared and set it equal to both of my masses added together times g times my h that I'm solving for, that delta y. What we want to note is this, that the total energy present at the end is different than the energy present in the spring. It's not okay to set the energy present in the spring equal to the energy present at the end because the collision steals some of that energy. We need to instead kind of break it down into steps Energy stays conserved as long as there's not an outside force, as long as there's not a collision, as long as nothing is dissipating it. So in the beginning in green, the energy stays constant. During momentum, because of that inelastic collision, there's a little energy lost. You're going to use momentum during that collision in order to solve for your new speed. So you use momentum to solve for the speed after. And that's how you'll know how to solve for your kinetic energy after. We could even figure out how much kinetic energy was lost if we wanted to. But what we really need is that kinetic energy that's still present after the collision, because the kinetic energy that's still present after the collision, that's what turns into gravitational energy at the end. And so you have to be very careful. You can't just skip intermediate steps. We're not allowed to just say, go from the beginning straight to the end if there's a collision in between, if there's an outside force in between. That's when we would say, I need to break this down into these steps.